will start. I hope this video will be a big success on YouTube or somewhere. So, my name is Samuel Campos. I am a backend developer at Blip, which is the Portuguese company for the Paddy Power Betfair group. We basically do online betting apps and web pages. And today I will talk about the Java Microbenchmark Harness, which is a toolkit to write benchmarks. But not only micro-benchmarks, but benchmarks of all sizes. This toolkit has special features to help you track down small parts of your code and of your system. So this is not the only alternative. You can write benchmarks with other toolkits. You can benchmark test your entire system using things like JMeter and send your requests to your system. But this toolkit is pretty cool, and I will try to present you the main features while I am also giving you some examples and basic performance tips in Java. So this toolkit can be used on multiple JVM languages, not only on Java, but I will present my examples in Java. And it has basically an annotation-based API. But before getting into the details, let me just try to answer these two questions before I present you the toolkit. Why should we benchmark our applications, our systems, and can't we write benchmark tests from scratch without using any toolkit or framework? And why should we write benchmarks? First, we should write them because it is a way to compare different implementation alternatives, and who doesn't search on Google for different alternatives to implement the same thing and try to pick the best approach in terms of performance. Writing benchmarks also allows you to measure the degradation of your performance over time. As you start building and adding new features to your system, often you need to refactor features that already exist, and you need to change the code of your existing features to handle new things. And sometimes we end up losing performance on our core features because we are adding some fancy stuff to our system to do something else. So if you have a benchmark, if you have benchmark tests on your system, you can trade off what you can refactor to do something more, or what you should build from scratch in another system or another module. You can also use benchmark tests to ensure that you are able to meet an SLA. Imagine, for instance, you are building a payment system or a service that needs to respond in X milliseconds. You might ensure that if you will fail to meet that SLA because you did some change in your code, you might want to ensure that your build breaks without deploying it to production and releasing to your customers. Benchmark tests might also be useful to anticipate and to reproduce some issues, some errors that only occur when your system is under stress and with lots of requests to handle. who doesn't have that bug that appears only once a month, or in Christmas, or on Black Friday. Sometimes it's hard to reproduce those kinds of problems in your system, and you cannot afford to wait until it happens the next time. So it might be a good idea to write benchmark tests to try to reproduce that problem. And having this mindset of choosing the best approach, of testing your approaches in terms of performance, also helps you to be educated in terms of writing the best code at first. If you are performance aware, you will lose less time trying to find different alternatives, because you will get educated along this process. But we can write benchmarks from scratch, but we need to take several things into consideration, because otherwise it's easy to write bad benchmark tests, and benchmark tests that will give you the wrong conclusions about the problems of your system. So you need to be aware of multithreading. Nowadays, CPUs have lots of cores, and it's easy to get into the conclusion that your code is slow, but you are not testing multithreading correctly, or you are not measuring the right metrics or the right resources. And in case of JVM languages, especially in Java, you might miss the just-in-time compiler optimizations. So if you test your code running just once, the result will be much different from your code that runs a million times, because just-in-time compiler will optimize your code as it runs. We will see some examples of that later. And if you build a framework or a benchmark test from scratch, you also need to implement reporting of your results, because sometimes you need to act upon the results you get. And these are the things that JMH or other toolkits, but in this case, JMH already gives you, so it's easier to start with, and helps you focus on the important things. So regarding JMH, you can write benchmarks to get several different types of metrics. The first one is you can measure the throughput of your method of your module in number of operations that you can execute in a unit of time. You can also want to measure the average time it takes to execute your method. You might want to sample the time of some executions to get percentiles and stuff like that. And there's also another benchmark mode in which you can estimate your code performance without having JIT to optimize your code, because sometimes you might have parts of your system that run only a few times, but they are still important. So you can measure that using JMH, and you can measure the optimization from one call to another, in which just-in-time compiler starts optimizing your code, and you can check the optimization process, extracting this kind of metric. So let me start by a simple example. All of who knows what memorization is? Okay. Memorization is nothing more than a simple cache, at least in this case I will present you, to avoid wasting time doing repetitive operations that are expensive. In this case, memorization will be a simple cache that will cache the output depending on the input you send to a function. You can think it as a lazy loading cache. And it basically helps you trade CPU or I/O time in exchange for memory. This can only be used for operations that always produce the same results upon the same inputs. So you cannot use caches or memoizers for stuff that return different results or that have some side effects on your system. So let's jump into the first example. So in this case, I have a memorizer class. Okay. All of you can read the code. I have my memorizer class, which holds a map, which is my cache of inputs and outputs. I have two builder methods that receive a function that performs the computations that are expensive, and then I can tell this memorizer that if my function will be used by one or multiple threads, and if it is thread safe or not. Then I will instantiate the memorizer and return a new function that will check if the input parameter is on my cache or not, and only performs the computation if it is not. So let me start running the benchmark while I present you the basic syntax of JMH. In JMH, you will implement a benchmark methods to test the different alternatives you have you have to test. So each benchmark method will be annotated with the benchmark annotation. In this case, I am computing the factorial multiplication of a given number, in this case 100,000, and I am comparing the plain execution without using a memorizer and using a memorizer, and I will compare the results. So the test has already run. It tells me that using the memorizer factorial, I can execute one operation and it spends 10 to the minus 8 seconds per operation. And in case I am calculating the factorial every time, it takes 2.7 seconds per operation. So it's very different. This is just to illustrate the importance of you to write the best approach for your use case. So it's important for you to choose the right approach, because otherwise you will waste lots of resources and do very different things and very wasteful things. Another annotation that I want to talk about is the setup annotation, in which you can give some initialization code that will be run before each benchmark is run. In this case, I am initializing my memorizer, and I will talk about the other annotations in later examples. And in this case, I am telling JMH that I want to extract the average time metric. So I have all of those modes available, and in this case, I want to extract the average time. So let's jump into another example. Who knows Java knows that there are wrapper classes for all primitive types, and Java can can handle different things or primitives or wrappers in the same lines of code without you being worried with converting a thing to another. So this is quite cool feature in Java, but it has some disadvantages. I just want to stress out what they are. If you are not careful when your JVM is unboxing an integer wrapper into an int, or any other type will suffer the same thing. If your wrapper can have a null reference, and in that case you will end up in a null pointer exception. And if you want to compare values, mixing wrappers and primitive types, you might be aware that there are some strange behaviors like these ones. In this case, I have a long wrapper which holds the value 2. If I compare it using equals to the primitive integer with the same value, it gives me false. If I compare to the primitive long, it gives true. And the stranger thing is that JVM caches some instances of your wrapper objects. In this case, in case of the integer, it caches all the references between minus 128 to 127, and in this case it gives you true, and the other case gives you false. But what happens in terms of performance? So let's jump into another example in which I will run a simple test. Okay. While the test is running, I just want to show you two more annotations. You have, because I've talked about just-in-time compiler, you have optimizations that are running while your code is also running. So it's important to know that your tests should have a warm-up phase and a measurement phase. This warm-up phase, I can tell the number of iterations it will take and the time each iteration will take also. I will make two iterations of 1 second, and then I will start measure things for 3 iterations of 1 second in this case. And on this test, I am comparing I'm comparing these two alternatives. I have an integer, I have an array of 4 million elements, I think. 4 million elements, and I am filling the array with values that are equal to the index. I could fill with any other value, but in this case, the code is exactly the same, but on the first case I am using a wrapper class, and on the second case I am using an integer array. And as you can see, those kinds of things have very different results in terms of performance. Using wrappers, I can perform 72.3 operations per second, and the number increases a lot if I do exactly the same thing, but I use integers instead of wrappers. This is important to know that sometimes you are sure that you will never handle null values and will have always have values for your elements. So you might consider, if you need to store hundreds of millions of things, or you need to store very, very, very fast, you might consider using primitive types instead of wrapper types. And why let me try to explain why the performance is so different. In case you have a primitive array, you have a reference to a memory region which holds the values of your elements directly. And if you have an object array, you have a reference to an array of references. Each of the references point to a wrapper object that holds not only your value, but also a pointer to the class the object belongs. It holds a monitor if you need to control synchronization. And the size of these things actually depend on your CPU or JVM version. So that's why the performance of those two things are so different. Let's go into another example, which will present the case of logging messages. When you are writing log messages, and we all love to see those big log files or things happening in production in real time, you need to be careful to not write too much and to not spend too much effort trying to just write messages that you will look only if you have an issue or only once a month to collect some metric or so on. So be sure that you write your messages with the appropriate level. All the frameworks for logging have different levels of logging. And check your production configurations to ensure that you are not wasting time writing things like traces or debugs for modules or classes that are not relevant for your business and that you know that they are doing the right thing for sure. But despite that, when writing log messages, you should be careful to not concatenate strings directly. And why this is bad? Because if you do this, all the objects that you have on your log string the toString method of these objects will be called, and sometimes these objects are big and they have lots of attributes and lots of inner objects within them, and the toString method it takes too long to be executed. And if you have a concatenation like this, in fact, your JVM will need to allocate multiple strings until it reaches the final string. So correct way to do that is to use parameterized messages. Almost, I think, all the logging frameworks support things like this. In this case, if the debug level is not turned on in production, the toString method will not be called for these objects, and you will not having multiple string concatenations until you reach your final string. And just let me show you an example of different alternatives. Okay. While this is running, I will just talk you about the alternatives. The first one is concatenate strings directly, and the second one is using parameterized messages, write exactly the same thing, and just be aware that the debug level is turned off on this test, so I am not writing anything to any log at all. I am just building a string to discard it afterwards. And the last alternative is to check if the debug level is turned on or not before writing the string. In this case, it is not, so this condition will always be false. And looking into the results, if I concatenate the strings, I have a big performance loss, more than 6 times. If I use parameterized messages without checking the log level, I have much more performance, and if I have this if condition, it's the best approach. But the increase is not so big from one alternative to another, and this kind of conditions decreases your code readability, and they might be harder to maintain, because sometimes you might want to change the level of a given message, and in this case you will need to be sure that you change the condition also. So you might not want to use this approach on your code base, and I don't like it personally, but at least be careful to use a debug a debug with debug message with parameterized values. Just to confirm what happens in terms of performance, I have here exactly the same example, but I will connect a profiler to check what happens in terms of memory. So in this case, I am concatenating strings, and I start to execute, and I can see that in terms of CPU, I start to use some CPUs just to build those strings, and use lots of memory just to discard the same strings afterwards. If I change the implementation and do exactly the same thing again, okay, we can see that the CPU used is less, it's much less than previous one, and I will not use many memory to build big strings to be discarded afterwards. And you might consider this because your system, your JVM might be doing stuff just to discard afterwards, and if you are not careful, your machines will just burn your CPU, and you will lose lots of money just because of things like this one. Another example that I want to jump in is about collections and maps in terms of Java. They are great because they enable you to handle loads of data that you don't know the size when you are writing your code. And they are usually an advantage because they are simpler to use, and you don't need to allocate big memory structures by scratch. But sometimes you don't know the size of your collection, of your data, when you are writing your code. But when your code is being executed in production, you might already know the size of data. You might have that size already available. And if you do, you should set that size when you are initializing the collection, just to give a hint to the JVM to know how much memory it will need to hold your collection. And in this case, you will avoid expanding the internal arrays or maps that the collection uses. For instance, the array list in Java that all persons, I think, have used it. It holds by default, it holds an internal array of 10 elements. If you go above 10 elements, it allocates a new array with a bigger size. It will copy all the elements to the new array and discard the previous one. So this is done in an inefficient way, but there is still some overhead. So let's consider an example just to compare those things. In this case, I have a list in which I have inserted a value with the same value as the index of that element. It doesn't matter. It is a big list of 100 million or 10 million elements. And my code will receive the original list and reverse the order of the list. This is a dummy case, but just to show you the difference. In the first alternative, I initialize the array list without giving any size. And on the second alternative, I initialize the array list giving the same size as the original list. And as you can see, the results are very different. If I give the initial size to my array list, my JVM will execute 24 operations per second. If I don't give it, it only is able to execute half of those 24. So this is a simple thing, but if you already know the size because the size is on your request, or you are fetching some big some number of elements from a database or something, you know how much elements you are fetching, so you can give a hint to your JVM to better handle the memory internally. So let's continue. Everyone uses streams nowadays. They were introduced in Java 8. They allow Java to mix some functional style operations when you are processing your streams. But sometimes you are doing and choosing stuff probably without knowing which one is faster. So let's jump into another example in which I will compare let me start run because this takes a little bit of time. So I am using I have a list like the list I had before, and I want to check if some given element is on my list or not. And in this case, I will try to find an element that does not exist on the list. So I will need to check all the elements of that list. And I am comparing a parallel stream, a stream, regular stream, a loop, normal loop, and a classical loop with an index variable. And another annotation that JMH has is the parameter annotation, in which you can give different values for your tests to run. In this case, I am testing with lists of 1,000 elements and 100,000 elements. And each of the benchmark methods will run for each of your parameter combinations. You can have multiple parameters, and JMH will execute for all the combinations. So let's check the results. For 1,000 elements, the loop and the classical loop with an index variable had almost similar approaches. The fastest one was the loop with an index variable, and the stream alternatives were much slower than the loop alternatives. And sometimes you might think that parallelizing your algorithm will speed up your results, but in this case, the parallel stream end up being slower than the regular stream, because for a few elements you need to handle threads and context switching, and you don't benefit too much from parallelization. So parallel stream is not always better than using regular streams, but for the case of 100,000 elements, the parallel stream was faster than the stream, because the overhead of handling threads is not so significant as before, but it was a lot slower than using each one of the loop alternatives. In this case, the loop with an index variable was faster, probably because because JVM and your CPU is able to perform a loop unrolling and execute multiple iterations at once. But these are kind of examples that might be interesting. So, some guidelines to write your own benchmark tests. You definitely need a warm-up phase. I will show you a bit more about later. How do you know that your warm-up is completed or not? Your methods, benchmark methods, need to return the results of your computations, or store the results in a black hole object, which is a class that JMH provides, just to ensure that you do not end up having useless code, and just-in-time compiler is very smart and removes all that code because it does not produces any side effects on your system. So just be careful with that. JMH also have as profilers to know to help you know what's happening in your stack, or your garbage collector, or the class loader, or in case of just-in-time compiler compilation, the optimizations that compiler does as your code is running. And we were reading the human readable reports, but JMH allows you to have CSVs and JSONs to integrate with your continuous integration pipeline. So let's go back to the previous example. If I turned off my warm-up phase, I will just measure for 4 iterations. I will also turn on my compiler profiler, okay, and I will run the test again. And let's see what my compiler profiler gives me. It gives me, for each iteration, it gives me an idea of the amount of time the just-in-time compiler spent to optimize my code. And this is useful because for each iteration, you can see that number starts to decrease. So this might give you an hint that, in this case, a good warm-up phase would be 2 iterations or 3, just to ensure that your measurements are not taken when the just-in-time compiler is still doing stuff, and your test might be slow because of that. So I have said on the beginning of my presentation that sometimes benchmark your application might help you to reproduce concurrency issues and help you understand what happens when your system is under stress. So Let me give you an example. I will just turn off the compiler profiler and turn on another profiler that I will show later. And in this case, I have a simple class that is a configuration manager, which holds integer configurations for different configuration keys. And I have two dummy methods, one to retrieve the value of my configuration and sum one unit to it, and another method to update my configuration. This is just dummy code, this is not production ready. But someone told me that my awesome configuration manager will be used by multiple threads at the same time. So I thought that it would be a good idea to synchronize my configuration map. So that's why I've done this. So this way, my operations over the map will not have concurrency issues. But this code has a problem. Anyone can see what the problem is? Okay. Despite my operations on the map are thread safe, in this case I am performing two operations over the map in a non-atomic way. In fact, I don't need this remove because when I put something on the map for a key that already exists, the entry will be replaced. But this is just to provide you the example. If I call this method while this operation has finished, but this one has not started yet, I will end up having a null pointer exception because my get operation on the map will return null, and I cannot sum null to one unit. So it would be hard to write a unit test to spot this problem. So, but it is easy if you write the right benchmark test. JMH gives you another two annotations that might be useful, in which you can say that multiple benchmark methods will run at the same time, and this is the group annotation. You give a name to your group, and then you say to JMH how many threads, in this case 5 out of 7 will be retrieving the configuration and summing one unit, and 2 out of 7 will be updating my configuration with some random value. So as soon as I start to run my benchmark test and reproduce this workload, I start getting my error here, which would be hard to find with a unit test. So I will fix my bug, I will run again, and I can immediately see that my code is running okay. But I have turned on the stack profiler, which is another cool profiler that JMH brings, and this profiler writes at the end of the test, writes how much time the threads spent and which were the states of my threads. In case of this test, most of the time my threads are blocked, waiting for something to occur. And I immediately can see that when they are blocked, most of the time they are retrieving trying to retrieve some value from the map. So this might be useful for you to know which are the bottlenecks of your system, of your algorithm, And these kind of profilers that JMH provide, they are lightweight. They do not interfere too much with your performance results, with your benchmark results, so you can use them and test at the same time. Just to finish, JMH has a bunch of examples, much better than my examples. In fact, I took some ideas from there. So you might want to check this page of examples. And if you need the link, I can provide you at the end. Just some takeovers. Measure your performance. Don't guess it, because if you change your CPU architecture or your JVM version, lots of things might change. So some things that were bottlenecks in the past are not anymore. So it's always a good idea to measure instead of guessing, and start optimizing things that are not your problem. That's, for instance, you can use the stack profiler to know where your bottleneck is, instead of wasting lots of time optimizing parts of your system that are not your bottleneck. Use a profiler to find it and work on the biggest bottleneck first. So thank you for coming. There are questions? Okay. One. Yes, I think normally the results are in milliseconds, I think. You can most of the times you are not so interested in measuring two small things, but number of things you can execute in parallel. So I don't think you can, using JMH, you can go under the precision of your CPU, of your system clock. So, but you can measure the number of things you can do at once. That's probably more relevant for most of use cases. Okay. And any other question? Okay, so thank you for coming. Have a nice day, and if you want to talk, we can talk afterwards. So thank you.